Welcome, everybody, to the density homework. For today's homework, you're going to need to know that density is the mass of something divided by its volume. Specifically, you'll need to know that the density of water is 1 kilogram per liter, or 1,000 kilograms per cubic meter, and 1 gram per centimeter cubed. You'll also need to know that specific gravity is the ratio of the density of one material to the density of water. On the right, you see granite. You'll also need to know that the density of granite is 2.7 times the density of water. In the first question, we have to find the mass of a big granite formation. That's where we need to know the density of granite. We're given the volume of granite, and we also know that mass is density times volume. So we multiply those two things together and find that granite is really heavy. Moving to something that's not as heavy, we have a room full of air. We have to find the mass of the room. Well, if you Google the density of air, it's about 1.29 kilograms per cubic meter. And the volume of the room can be easily calculated by its dimensions. I get about 51 cubic meters. Mass is density times volume. Multiply those together and find that that's about 66 kilograms, not insubstantial. A far more substantial mass would be the mass of a bunch of gold bars to fill your backpack. The density of gold is 19 times the density of water. So there are the dimensions of a backpack that I found. And mass is density times volume. So if you tried to smuggle this much gold, you would have some problems. That's 2,200 pounds worth. Also, don't do that. I mean, there are other problems with smuggling gold bars. So don't do that. Here are two containers of an unknown fluid. One is water, rather. The other one is an unknown fluid, and we have to find its density. Finding the density of something is one of the ways you can learn about it and figure out what it's made of. So first we have to find the mass of each fluid by subtracting the mass of their containers. So I've got 63 grams of water and 54 or so grams of the unknown fluid. The question asks for the specific gravity of the fluid, so that's the ratio of the fluid's density to the density of water. Density, after all, is mass divided by volume. Volume cancels out, so really if you're dealing with the same volume, the specific gravity is the ratio of the masses. So the specific gravity of the fluid, because they are both in the same volume, is the ratio of their masses. And I get about 0.85 or 85% as dense as water. Antifreeze is less dense than water, and to use antifreeze, you mix it with water before you pour it in your car. Now, those of you who've done this before know that the mixing ratio is actually a 1-to-1 volume ratio, but here we are. This person is mixing it differently, I suppose. To find the density of the mixture, we need to know the mixture's mass and volume. The mass of the mixture is simply the mass of water plus the mass of antifreeze. However, we don't know either. We know the volume of the mixture, but not its mass. So we can use the fact that mass is density times volume. Multiply the density of each fluid times the volume that's being used to find the whole mass of the mixture. Is about 8 kilograms. So now that we know the volume of the mixture is 9 liters and the mass of the mixture is 8 kilograms, we can find the density. A little less dense than water. All right, now begins the pressure side of the homework. First off, my daughter tiny heels compared to my boot. No, those aren't her heels. Those are just sneakers. That is technically my daughter. She's the one in the sweatpants. Pressure is force divided by area. She weighs about 350 newtons, and that's the area of her single heel. So when she stands on one heel, she exerts 350 kilopascals against the floor. When I stand on two boots, I exert a pressure of 6 kilopascals against the floor. That is a beautiful swimming pool. It's not mine. The pressure at the bottom of the swimming pool, the absolute pressure, is atmospheric pressure plus gauge pressure. So the pressure that the air exerts plus the pressure that the water exerts. And the air exerts 10 to the 5th pascals, and the water exerts rho GH against the bottom of the pool, for a sum of 1.2 atmospheres of pressure, or 1.2 times 10 to the 5th pascals. But what force does that exert against the bottom of the pool? To find the force, we need to know the area of the bottom of the pool. And the area is its length times its width. That is a large pool. Or a whole lot of newtons. The next question also involves pressure, but there's one bit of cleverness that we need to figure out. And that is that in this U-shaped tube, where these fluids are completely at rest, the pressure at point A in this diagram equals the pressure at point B in this diagram. Pressure in a given fluid is the same at the same depth in that fluid, and points A and B are at the same depth in the water. So the pressure exerted by the yellow fluid on the left equals the pressure exerted by the column of water above point B. What that means is that rho GH from the unknown fluid equals rho GH from the water. Well, we know an awful lot of these numbers. We don't know the density of the fluid, but we know the density of water, the height of the column of water, and the height of the unknown fluid column. We know G, but it algebraically cancels out on both sides, so I didn't throw that into the calculation. I put in the numbers that I have, and I calculated a density less than water. Unsurprising, because it takes more of the unknown fluid to compensate for the pressure of a small column of water. All right, in the next question, there is a water tower on top of a hill, and the water tower flows water down the hill through a pipe that sprays water up into the air. That's the second coolest water tower I could find. The coolest one looks like a peach, but I couldn't find any cool photos of it. All right, to find the pressure at the ground, we need to know the height of the water. Well, the height of the water is the height of the water tower plus the height that the water tower is up the hill. The hill is 100 meters long, it's a 30-degree angle, 100 sine 30 is 50. So the height of the water tower, or the height of the top of the water, is 65 meters. The pressure at the bottom is rho GH. So I know the density of water is 1,000 kilograms per cubic meter, gravity 9.8 meters per second squared, and the height of the water tower that we just found is 65 meters. Multiply those together, and I get about 6.4 atmospheres. Okay. The follow-up, though, was asking, how high does the water burst out of that pipe? And the clue was, the water flows without any friction. That means energy is conserved. And if energy is conserved, the water goes all the way back up to the top. All right, I hope this solution set worked out for you. I hope you found the homework easy to follow. And I look forward to moving on with fluids.